yourself and quickly.
I'm Andrew Martin, and I'm a data scientist here at Logojoy. Today I'm going to be talking to you about the progressive growing of GANs paper that was written by Kiris et al. From NVIDIA Research about a year ago. This paper presents a new training methodology that allows the authors to get some really impressive results. When you look at what people usually get from GANs, there's a lot of blurriness, there can be little variation, but the results that these guys got using their progressive growing GANs technique are really almost unprecedented. So just as an example, these are some fake celebrity faces that this GAN model generated. So the resolution is extremely high. The symmetry of the face is human-like. It really takes a long time of looking at these to see what's kind of fake about them. So when it was published, it created this big stir because they also put out a 5-minute YouTube video where they interpolate through the latent space, and you get to see all these faces devolving and morphing into new faces. And it's really pretty creepy and bizarre when you see how that actually works. This paper is interesting to me because, like I was saying, one of the projects that I work on here at Logojoy is generating typefaces. And this is a computer-generated typeface that I've made in recent weeks. And the progressive growing of GANs training methodology really jumped out at me because you're able to get really good results with only one generator and discriminator. It's a really simple GAN formulation for the results that you get, and I'll get into that later on. But this is just an illustration of how the training evolves if you're doing typefaces. So it starts very low resolution, and over time it gets gradually higher resolution. This is at the Minibatch level. If you're looking at it in actual size level, this is what the training looks like. So you're starting at 4x4, 8x8, 16x16, and eventually jumping up. So in this talk, I'll move over a quick introduction to generative models and why there's motivation for having this progressive growing GANs formulation. I'll then go into the progressive growing of GANs model. There's the training of that, and then the second part is the modeling techniques portion of the paper, where they introduce some interesting normalization and variation increasing techniques that hadn't been seen before. From there, I'll look at evaluating the progressive growing GAN. And this one, it's an interesting section. It's a little contentious. Michael might have some comments on it later. But because there are so many things coming out of this paper, it's not a long paper, but it's a very dense paper. And the researchers are putting a lot of different things, and they probably failed a lot of times trying things that isn't really described in here. So evaluating what actually makes these results good is not simple. And it's something that we're going to talk about.
On the previous slide, the thing you showed us, was that using this model?
Yes.
Did you use this? So did you use it like exactly, or did you modify it in any way?
That one, it's pretty vanilla. I changed the feature map dimension because the memory usage was getting out of hand.
There's a footnote where they say what the actual hardware is that they're using, and it's their like $200,000. No, yeah, they're like, oh yeah, we just used this, and I was like, yeah. So that makes sense.
Yeah, but I've also done some stuff of taking the generator out and putting it in a different model, which I could tell you about later. And then we'll wrap up with conclusions, and I'll introduce some discussion points that we can dive into in the second half of the talk. So the way the authors present it is your initial problem is you want to generate high resolution images that look realistic and with good variation. And they present the 3 options that are readily available today, and they find them all lacking. So you can have autoregressive models, which are things like pixel CNN and pixel RNN. You find that you can get sharp images with these models, but the training is not that reasonable yet. It also has the disappointing side of it where there's no latent space. And for a lot of the work that makes these GAN models exciting, a latent space is a huge part of it. Because once you have that latent space, you can sample from it, and that's where you get really cool results coming from. You have variational autoencoders, VE for short. These are really fast to train. They're nice because conceptually they're quite straightforward, and they're pretty simple. You can put together a VAE pretty quickly. The downside is that it's really hard to get sharp, high-resolution images with a VAE. There's been a couple recent papers that suggest that there are links between variational autoencoders and GANs that can produce really good results, but those are papers from like July. It's really pretty new. Even though there's also some older stuff, but that older stuff on GANs and VAEs isn't quite as good. Then finally we get to GANs. And GANs are cool because they give us sharper images than all the other ones. The downsides are typically they're low resolution. Most of the papers report results on 64 by 64 images, maybe 128 by 128. And there's this open question of how much variation are the GANs actually capturing. A lot of people who have, in their own time, played around with GANs or played around with them at work, find you'll often get serious mode collapse, and it'll take a lot of time to get out of that mode collapse. In some data sets, it seems like there's nothing you can do to avoid mode collapse. So there's this big issue of how easy is it to replicate results in GAN papers. The other thing is the unstable training, where the generator and discriminator, they just can't line up very well. Okay. Cool. So just a quick introduction to GANs. The way it seems like most people are familiar with GANs, but really briefly, the way GANs work is we have a data set, and we're interested in learning the probability distribution of that data set. We can't actually know it, we can only sample from it. So instead of learning the probability distribution of the data set directly, we create a generator which, over time, through adversarial training, learns how to take random noise and convert that into an image. And we use that generator to approximate the real data distribution. Adversarial training means we have two neural networks. We have a generator and a discriminator. The generator starts with random noise, and it creates increasingly better images with those. And the discriminator gets fed real images and generated images, and it gets trained to distinguish between real images and generated images. In theory, when the generator and discriminator hit equilibrium, it's a two-player min-max game. When they hit equilibrium, you'll have the probability distribution of the generator equal to the probability distribution of the data set. That was the theory that was laid out in Ian Goodfellow's 2014 paper, and it's a really nice theory. You know, when you read it, you're like, this is some of the best machine learning theory I've ever read. Once people started to work on it and to try to get that theory into reality, that's when everything else in GAN research happened. So in theory, when we hit equilibrium, we should have this, but we rarely hit equilibrium. Even if we could, the results might not be good. And the last 4 years of GAN research have been trying to get to this.
Can you talk a little more about that? Like, what is preventing you from getting to equilibrium, and what do you mean by results not being good?
What was the second part?
And what do you mean by results not being good?
Okay, so it can be hard to get to equilibrium because when you start off GAN training, you have the distribution of the generator and the distribution of the data are very different. Because the initial passes through of the generator, it's just random noise. So it's really easy for the discriminator to get too good at identifying real versus generated images too early on. So the generator never gets good gradient signals on how to improve. The discriminator can just say fake, 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 real, and be perfectly accurate with it, so no training actually happens. And this can happen at the beginning of training. It can also happen as training progresses. You can find they diverge over time. So this is the main reason for that. And by results not mean it being good, what I mostly mean is results haven't been consistent. In that it's, even when training seems to converge, it doesn't always mean that the images you're going to generate because of that converged training will look good.
Yeah, there's a pretty big gap between the formalism and actual quality. I think there's one way of viewing it, which is what you're saying.
Exactly.
Sorry. By equilibrium, you meant like generated data is like looks exactly same as the data, or looks like it?
It means, in GAN language, it means that the discriminator is wrong 50% of the time.
Do they hit the equilibrium when there is good quality images generated? How far from it are they?
So you can generate really good quality images with nothing close to equilibrium. You can have a horribly divergent GAN and the images can still look good. And you can also get to something that converges and the results aren't that good.
So you can see the breakdown in the form.
I see that pattern in Vase also, and the elbow loss. Like it just don't make sense. Sorry, slipped in.
As comparators.
It was compared. Hush.
So
You should have a coin jar for.
The authors identify that there's 4 main challenges in GAN training. I've talked about this a bit, but it's a really important one. If there's not much overlap between the training and generated distributions, then gradients can point in random directions, which means that it's hard for the generator to learn. Second problem is that the generated results, when learning does happen, can often exhibit very little variation. In the literature, this is called mode collapse, and it's another open problem. In GAN research, it's even an open problem to figure out when it actually happens. High resolution GANs are a lot harder because you can imagine if I'm training a GAN on 64 by 64 images, fairly low resolution, my generated images will look a lot more similar to my real data than if I'm doing 1024 by 1024. Because there's a lot more detail, there's a lot more high frequency information for the discriminator to cling onto to be able to quickly identify what's real and what's generated. There's also this point of, just from computational memory perspective, if you're generating higher resolution images, you need a smaller mini-batch, and this can destabilize training.
Quick clarification. The first one, mode
Yes.
collapse. I know we may have asked it earlier on in the earlier talk, but why is it called mode collapse? Gradients going in different directions.
So mode collapse is little variation in results.
Oh, it's a variation? Okay.
Yeah, and that just means the data is multimodal and you lose some of those modes.
Gotcha.
This is how they introduced the progressive growing of GANs model. It's meant to tackle all of these challenges. The authors say that their key insight is that we can grow both the generator and discriminator progressively, starting from easier, low resolution, and add new layers that introduce higher resolution details as the training progresses. So immediately you can see how that addresses that first big challenge that they identified, where low resolution training, the generator and the real data, the distributions are closer together. And as you get training signals to the generator and the generator improves, you add more, and then you can up the resolution this way. The details of the implementation are that you first discover large scale information, because also at lower resolution images, you're getting more of things like outlines, you're getting more structural information. Whereas as you go higher resolution, you're focusing more on high frequency detail, things like eye color and skin texture and hair and things like this. They increase the size of the generator and discriminator simultaneously. All the layers are trainable throughout, and this will be more obvious when you see the diagram, but you start at low resolution, and when you add higher resolution layers, you keep those low resolution layers trainable. You don't freeze them, which is a reasonable intuition that someone could have. And then there's this fourth point, where new layers fade in smoothly. So as you're at 4x4 and you're moving to 8x8, you don't just make a jump all of a sudden to adding the 8x8 layers. You go through a transition period where you upsample some of the 4x4 images before passing them to the discriminator, and then you pass some of them through the 8x8 layer. And again, this will be way clearer with a diagram. So here's a way to look at the model. The first iteration of the generator and discriminator, we're just using 4x4 images. And the thing with 4x4 images is, it doesn't matter if it's real or generated, they all kind of look the same. So it's pretty easy to get from this step to this step. There's an added benefit here, which I'll touch on a bit later, but because the model starts with really low resolution, you're able to pass a lot of images through faster. And this supports one of their claims that this model is a lot faster to train than comparable models. So we start with the small low resolution and go to the high resolution. We add in another layer. You see the image gets slightly more clear, a little more resolved. And then we continue on, and eventually we get to 1024 by 1024, and we get these images of people that look oddly familiar, even though you don't know any of them.
One of them has a half beard, just saying. Well, two of them, actually.
Oh, no, very good.
That's it.
So this gives a really nice way to just see how you start really low resolution, and at the end of it you get high resolution, and it's able to do this all in one model. We can talk more about that in the discussion period. I mentioned that new layers fade in, and this is
Just a clarification on the previous slide. Do you need to keep the model which you're building and stacking on top of each other, or each layer is independent from the previous layer?
So
Can you repeat the question?
Can you repeat the question?
Yeah, sure. I guess you're closer to
louder.
that. Oh, okay. So my question is that do you need to keep the models as you grow and you progress, or each layer is independent from the previous layer?
So all the layers are independent of each other, but you keep the entire model throughout training. So it's the same model, you're just adding new layers to it.
Oh, okay.
But they are not frozen, the previous one.
Exactly.
Okay.
So that if you get information that suggests they should update, you can do that too.
So essentially you're given it a better starting point by doing that?
Yeah, that's one way to think about it. They talk a lot in the paper about unhealthy competition between the generator and the discriminator. And this is a way to level the playing field in early stages of training.
So can you just talk about the bottom part, of the bottom pyramid here? So I guess that's the discriminator, is that right?
Yeah, so what this is showing is just that the discriminator grows at the same rate as the generator does.
Okay, but it's always making its classification at the 4x4 stage?
No.
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 It's upscaled with the model.
Okay.
Warren, you're first.
Yeah, I mean, from the latent to format to 4 and from format 4 to 8 multiple 8. So the real to 8 multiple 8 means you compress the real and put the input to connect to the 8 multiple 8 layer at the same time.
Could you repeat the question?
The second column.
Yeah.
Like say from the latent to 4 multiple 4, the layer, and then 8 multiple layer. So 4 multiple 4 layer will connect to 8 multiple 8 layer.
Yeah.
Also the real, you compress it, the real image, and to 8 multiple 8 image, and put the input to the 8 multiple 8 image.
Yes. So you'll see in the next slide, there's an upsampling step between layers.
Mm-hmm.
And you adjust the real data to be whatever size the discriminator is currently accepting data at.
Mm-hmm. So the 2 8 multiple 8 is the same layer or different layer?
Here and here?
Yeah, the same.
So it's added at the same time, but the generator's 8x8 layer is independent of the discriminator's 8x8 layer. You had a question?
Yeah, so on the note of unhealthy competition,
Yeah.
And you earlier on mentioned that if in the very beginning the discriminator is just like perfect at distinguishing what's real and what's not, like how does that translate to the random gradient directions? I'm a little lost on that.
Okay, so the way the generator and discriminator adversarial training dynamic works is that the discriminator is learning at the same time as the generator.
Right.
So the concept is that early on the discriminator is not very good. So it fails a lot when it's trying to pick real images from fake images. So sometimes the generator will trick the discriminator early on, and it will get a signal that yes, this image is good.
Right.
If it doesn't get those signals that yes, this image is good, then the gradients aren't necessarily meaningful and won't give the generator information that it can use.
So you want the discriminator to grow with the generator?
Proportion.
Okay.
Yeah.
Idea.
Right.
My question still is actually, one thing I always wonder with this paper we showed is when it goes from 4x4 to 8x8, does it recommend a standard approach for how to fill in like the extra like pixel density?
It's just the nearest neighbors.
Yeah, I think it's just the nearest neighbors.
I think.
That's the only thing I always wondered, because there's different ways to fill in the gaps and to do the color approximation when it stretches out. I'm just wondering how that hits like a add-on to his.
Yeah, that's not something people usually talk about.
Yeah.
I think they just assume we'll do nearest neighbors on it.
For upsampling, right?
Yeah.
Okay.
Or, yeah.
So this is how the layers fade in. And in the paper, they don't give nearly as much discussion on this as I'd like. They don't spend a lot of time motivating why you need to fade the layers in. They say it's to avoid sudden shocks, which intuitively makes sense, but there's not really any body of work that they point to that suggests that you would want to do that, and they don't indicate that they tried other things and that it failed. So here what it's showing is we have a generator that's at the 16 by 16 resolution, and then we have this block which means 2 RGB, which is just taking the latent code and turning it into an image. And on the discriminator side, we're taking that latent code, or we're taking that image and turning it into a latent code. When we want to take 16 by 16 and move it to the 32 by 32 resolution, we create this alpha parameter. And alpha goes from 0 to 1, and as training progresses, alpha goes closer to 1 until when it's at 1, the new layer is fully faded in. So we pass our data through the 16 by 16 layer. We upsample it 2 times, so it is 32 by 32. Then the proportion alpha gets passed through the new 32 by 32 layers, while the proportion 1 minus alpha does not get passed through the 32 by 32 layers and just goes directly to the discriminator. At the same time, the opposite process is happening in the discriminator, where you're having some of the images go through the new 32 by 32 layers, and some of the images just get downsampled and passed to the 16 by 16 layer.
Just one question about that. This is 16 by 16 by 3, like 3 channels?
Yes.
Yeah, the way that they do the paper, it's 3 channels.
So alpha is a learnable parameter, right?
No.
That's the weird part.
Alpha is just like it gradually increases as training.
Linear interpolation.
Yeah. When you're working with the model, there's a parameter that's just like set when alpha increases, and it's like every 100 steps alpha increases 10% or something like that.
Yeah.
Well, it's across 800,000 steps, I think, in this case.
Right, 100, 800,000.
The beauty of very expensive technology.
So,
Bilal.
So the training time varies from layer to layer?
Yes. So you're like the 4x4 trains a lot faster than the 8x8, and the 8x8 is faster than the 16 by 16.
But it's the same number of epochs.
Okay.
Yeah. They each see, I think, 10 million images.
Yeah, or something like that.
Do you use a different batch size for? Oh yeah. Okay.
Yeah.
It's
Because
not like that.
you can imagine by the time you're at 1024 by 1024, if your batch size is still 32, you're going to need a lot of
I think it's
compute.
4. I think it goes down to 4, or is it?
Yeah.
I think it's
For me to even get to 256, I had to have 256 at 1.
right.
Like I couldn't even get close.
So each additional layer basically training through the fixed number of epochs.
Yes.
And then you progress on to the next.
And then you start fading in the next
And
layer.
by the last epoch, the alpha would become like, I guess, entirely to 0 or entirely to 1, whichever.
Yeah.
Yeah.
So you can think of it like we feed a certain number of images through the 16 by 16. Then once we get to a certain point, we start fading the new layer in. And then once it's faded in, we feed a set number of images to the next layer.
Okay.
Can you just reiterate the justification they gave for for doing this transition?
Yeah, absolutely. So their justification is that they thought if we take the new layer and just stick it in, then all of a sudden we have all these just initialized parameters, and this might cause a shock to the model and potentially make training unstable.
Just as a quick qualifier, that is true. Like if you do just add layers, the thing just explodes like immediately. So it's
cool.
It has to be the softest introduction,
like
basically.
ever. Yeah. Hence 800,000 steps is the fade time, right?
Right. And is this something that they've introduced, or this is like a standard?
Nope, not standard.
No, it's not standard at all. They talk about not GAN research that's done it, but other areas of research. I wasn't familiar with it. There's like a neural gas model that they talk about that fades in layers. Yeah,
I don't know.
it's not a common thing to know about. But they contrast it with, say, the stack GAN way of doing it, where you just have everything there, and you're training different resolutions with different models. So, again, just showing this GIF. This is how the training progresses, where you have small and it's just getting gradually bigger over time. Touching on the loss functions that are used in this paper, they say their work is, it doesn't really matter what loss function you use. It's more a training procedure, and as long as you use a reasonable loss function, you should be able to get good results using it. To illustrate this, they use 2 different loss functions. They use a Wasserstein GAN with a gradient penalty, and they use a least squares GAN loss function. The Wasserstein GAN results do look better, but I think that's just a function of it is a better loss function. But they make a point to say that you should be able to use this with different loss functions, and it shouldn't be an issue. So some of the benefits of this. First one, the training avoids the problem of too much difference between the generative distribution and the real data distribution in early stages of training and in later stages of training. And the reason for this is that the distributions between the low resolution images are a lot closer between the generator and the real data, and as you get up to higher resolution images where differences become more apparent, you've already trained your generator and it's already at an equilibrium kind of state with the discriminator. They say the training is 2 to 6 times faster than it would be for other models, and the way they justify this is because with other high resolution models where you start at, say, 256 by 256, you have to pass all the images through the network at that high resolution, and it takes longer to pass a high resolution image through the network than a low resolution image. So because a lot of early training steps are done on very low 4 by 4, 8 by 8, 16 by 16 resolution images, you can get a lot more information into the network faster. Another benefit they talk about is that you're only using 1 GAN. Other models that have achieved comparable results tend to have a series of GANs stacked on each other or have some kind of hierarchy of GANs, and this becomes challenging because you have a lot of moving parts. It can be very computationally expensive, and training can be very difficult. And the final part they point out is you have more stable training. You get a lot of steps done at low resolution where the training is just by its nature more stable, and you avoid some of the problems that other high resolution models have, where if you're starting at 256 by 256, you have small mini batches the whole way, and this can make your training less stable. So it's nice when you can have larger size mini batches with smaller resolution images, and you can get that nice stable training early on. Here I'll introduce 3 of the noveling modeling techniques that they use in the paper. After this, in the evaluation part, we'll look at an ablation study that they do, where they try to identify the contribution of each of these different techniques. So the first one they talk about is mini-batch standard deviation. And they introduce mini-batch standard deviation by talking about mini-batch discrimination, which is something that was introduced about 2 years ago, where in the discriminator, just before you discriminate between the generator and the real data, over the mini-batch, you compute some statistics, and you concatenate those on as feature maps to your output vector. And you're discriminating on those statistics over the mini-batch as well as the actual images. And the motivation behind this is we want to avoid mode collapse. And a way to think about mode collapse is you're losing variation in the data, but another way is the generator probability distribution looks a lot different than the real data probability distribution. So they're saying if the statistics over each mini-batch between the real data and the generator are similar, and the discriminator learns to identify that, by definition we should have more variation in the generator results because the distribution of those statistics would look similar to the data. In that mini-batch discrimination that they introduce, apparently there's a whole host of stats that are computed, and it's somewhat unintuitive and not very easy to do. Yes?
So they literally just like concatenate the stats along with the Z input vector? Sorry, the feature.
In the code, there's just like compute the stats and then just like concat.
Okay. And the stats are just variance.
Yeah. So here the stat, so what they propose with mini-batch standard deviation is they say, and Michael's helped me with this, talking about this a bit, but what they're really saying is just, it doesn't matter really what information about the mini-batch that we have, we just need some information about the mini-batch. It doesn't have to be very detailed, it doesn't have to be very complicated. All we need to do is, so how they implement it is, they take the mini-batch and then they divide it into groups. And in the paper they refer to groups as spatial locations, but there's no real, the groups are just the mini-batch split into pieces. There's nothing really spatial about it. So then you compute the standard deviation over each of these groups, and you take the average of it, and then you tile that across the groups and across the pixels, and then add that onto the mini-batch. So they like mini-batch standard deviation because they find it a lot simpler, and it achieves the same goal of forcing the generator to create generated images that have similar, standard deviation to the real data. Yeah, and this is the process.
By spatial location, you mean?
I think it just means pixel.
Somewhere in the image?
I think it just
Maybe
means
they're
pixel.
talking about pixels.
I think they just mean
because they also split it into groups, and I was wondering about that, but it's probably.
I don't remember the group piece, but I mean, in the original paper, they actually have a window that's basically moved tiling, but like, but I believe it's it's just the pixel by pixel. Yeah.
Maybe the groups are the window then.
Yeah.
So for features, is it talking about the pixels of the image, or is it defining features?
It's just like an additional vector of features that they add onto it.
Yeah. Oh, okay.
Yeah, I mean, it's also not exactly a pixel either because you're quite a ways up. Like they put it way at the end of the
feature space.
Well, I guess it is because you're in the discriminator, so it's roughly a pixel. Yeah.
So is this calculation happening? Does it happen in generator or discriminator?
Discriminator.
Oh, okay.
So it happens just at the very last step of the discriminator.
Okay.
If any of you remember back to the StatGAN thing, remember how they were concatenating the text embeddings at the end? This is very much the same thing, but you're doing image statistics instead of the language stuff.
So the very end, is it because the discriminator is generating, say, a 4x4, and then it makes a call, makes a decision, right? Whatever input size the discriminator is generating that before doing that before making the call. Is it it's a fake or a real one? Is that correct? If you go
right, I think they started at 16 by 16.
Okay, so right before at 16 by 16 at discriminator, then it's adding
this statistic
right
slice. It's not exactly right before. I think there's a
4x4 by a lot of channel states.
Yes, exactly. Yeah. So it's not because you're technically still in these convolution block things, so you're not actually at the. Yeah, it corresponds with 16 by 16, but it's right before it becomes 16 by 16.
So it adds it to other channels then, like channels specifically for the SDs then.
Yes.
Mm-hmm. Okay.
I think
that's fair. That's
and it's a later evaluation metric that happens at 16 by 16. These should be there throughout the training.
Okay.
Yes.
Sorry, can I recap that question? So the answer to what you asked was that they add stats as an extra channel on top of the 3?
That was a question.
So at the discriminator layer, there's probably close to 1,000 channels by that point. 4x4 by like 1,000 deep. Starting from the 3x3 image at the start of the discriminator, or like at the input layer for the discriminator, and then gradually as it downscales the resolution, it's also scaling up the number of channels.
Exactly. Yeah. And then it just I think they do add a channel to the end.
Exactly.
Yeah.
Okay. So whatever many channel, like you have n channels, n plus 1 is the stats that come from what you just described.
Okay, so one channel is manually added at each layer.
So it's not at all pixels. I was wrong. I was reversing the generator and the discriminator in my head. Because you're in convolution space at that point, right?
Yeah, because if you add to the pixels, then the final image is sort of disrupted. So because it's not the same like 4x4 or whatever.
Remember, in the discriminator, the final layer is just a one value, and it's true or false.
Sure.
Right? Because you start with the embedding space, you go to the image. The discriminator is the opposite. You start with the image and you go to the.
Yeah, that's why I asked. Because right before you have a 4x4 or whatever.
So it's at the end of that, which I mean, you may have the figure. Do you have because they do show. There was I think it doesn't matter.
Right.
Yeah.
Cool. Seems clear.
Okay.
Sorry, I was backwards in that.
Next, they talk about normalization and their motivation for adding 2 different methods of normalization is that because of this mismatch between generator and discriminator that we've been talking about all evening, in the generator you can get increasing gradients at times, and they find you need a way to rein them in. There's been other papers where they say covariate shift is the real problem here, and it's something that I looked into, but I could never really get a good hold on what they mean by that. In the discussion later on, we can potentially dive into that. They say, don't worry about covariate shift. This isn't the problem here. We really just need to make sure we don't get these really large magnitude gradient updates. So, to this end, they talk about equalized learning rate and pixelized feature vector normalization. Equalized learning rate, we're saying with adaptive optimizers like Adam, the dynamic ranges of parameters determines their learning speed. From there, we have parameters with larger dynamic ranges can take longer to adjust, and thus they can either have a learning rate that's relatively too fast or too slow. The authors implement equalized learning rate by using a trivial, normally distributed initialization and then they scale the weights at runtime. This takes advantage of scale and variance of these adaptive optimizers, and they say leads to benefits in the long run by keeping the generator updating consistently and giving parameters equal learning rates, even though they might not have equal dynamic ranges. And this is a little tricky to begin with, so I don't want to spend too much time on it now. In the discussion side, we can bring this back up and really dive into it.
So it's just a quick summary.
Yeah.
It's not the global adaptive learning rate, it's the local individual learning rates that could not necessarily co-vary.
Yes.
Okay. And they have some way of implementing it.
Perfect. The other one is a lot simpler and more straightforward. It's just pixelized feature vector normalization. And they noticed that in their training, you generally have reasonably behaved gradients, but every once in a while you have a really spiky gradient, and that can throw training off. So all pixelized feature vector normalization is just saying, don't let gradients get above a certain value. If they do, just normalize them to 1. So they like this because really light footprint doesn't change behavior 99% of the time. It's just when you do get those spiky updates, it flattens them out. So now we get to look at how we evaluate the results of this GAN. And the GAN literature is unique in that every time a new model is introduced, a new way to evaluate models is introduced. So we can get a taste of that.
How do you confirm each other?
Yeah. Don't even get started.
We'll have a discussion.
So the authors take as their starting point multiscale statistical similarity, and this is a way to compare how similar two images are between each other. And it goes way back into image processing before deep learning days. What people have found, and this has been cited numerous times, they talk about it in the StackGAN paper, they talk about it in this paper, is that MS-Sim, while it's good at looking at global similarity, it's not really good at looking at local similarity. So it can be hard to assess whether the GAN is picking up different modes relating to things like finer details, maybe tones or textures, things that are really high frequency information. So what the authors do is they propose something like MS-Sim, but doing it at multiple levels of resolution simultaneously. And they're hoping that in this way, you're able to capture the really structural, global kind of structure at the low resolution evaluation, and then at the high frequency ones, you can focus more on those local details. The way they do this is they sample from more than 16,000 images, and they extract 128 descriptors from each level. A descriptor is just a 7x7 neighborhood that goes through the 3 color channels. You then compute the sliced Wasserstein distance for training images and generator images based on those descriptors for each of the images. In the paper, this method has a lot to recommend it. The authors present an ablation study where they evaluate the contribution of the different modeling techniques and try to get a sense of what's actually contributing to the results we're getting. This column shows we're using the CelebA dataset, and the CelebA dataset is a dataset of celebrity faces. There's actually a massive contribution in this paper that is in the appendix. It's that dense, where the authors took the CelebA dataset, which I think is 128 by 128, or has a variety of different image resolutions in it, and they made it CelebA HQ. So they use these really interesting image processing techniques to take all the images, zoom in on the face, and upsample it to 1024 by 1024. Which is a really not easy thing to do from an image processing standpoint, and they mention it as an offhand. By the way, we did this too. This one is looking at the bedroom data set, and the bedroom data set is at 256 by 256. CelebA is at 1024 by 1024. And the table is showing you the sliced Wasserstein distance at the 128 by 128 resolution level, 64 by 64, all the way down to 16 by 16, then the average of that. And it's also showing you the multiscale statistical similarity.
How many images?
How many images?
16,000.
16,000.
Each?
Yes. Oh, well, these
16.
are all done over the same 16,000. So what you'll notice with MS Sim is that it doesn't improve when the results improve. So the first line is before we've done anything with the current paper. They took the GAN model from the original Wasserstein gradient penalty paper, and they just ran that with their new data set. Then they add the progressive growing training. Then they look at what happens when you add a small mini batch, and small mini batches are toxic to the training. Then you look at revised training parameters, what happens when you add mini batch discrimination, what happens when you add mini batch standard deviation, which is what they contribute. They look at the equalized learning rate and pixel-wise normalization, and then they look at a converged model. So all of these models, they don't run them to convergence. They just pass 10 million images through them, and they do this because they want to amplify the differences between different stages. So if you look at multiscale statistical similarity, you have Gorajani et al., and the score is 0.28, and you have their converged model, and the score is 0.28. So this is what Gorajani et al. Looks like. This is what the converged model looks like.
Oh, wow.
It's not a good metric when you're scoring those exactly the same. The nice thing that this sliced Wasserstein distance has going for it is that the average tends to map well to the quality of images generated in relation to each other. Now, this is hard to say definitively because the authors pick the images that they show on this slide. It's not just random. They picked ones that are probably illustrative of what they want to illustrate. So it's not definitely perfect. It's not definitely great, but it is encouraging. So here you can see you get lots of improvement here. This is when you use the small mini batches. And you just lose everything. And it gets harder as you get to this side, where you start adding those pixel-wise normalization, mini batch standard deviation, and equalized learning rate. But the converged example is definitely better than any of the preceding ones.
Did
Yes.
they keep the small mini batches and keep adding other stuff on top of it, or did they just not include that one?
So the small mini batch, I think, was just to illustrate how bad small mini batches were.
Okay.
They did that, and then they went back to what they normally do. Yeah.
But this also uses small mini batch, right?
It uses small mini batches once you get to high resolution images.
But the lower one usually.
Lower ones use 32 by 30 or 32 mini batches. Yeah.
Can you just explain the Wasserstein distance again and what exactly is being compared when you take that?
Okay. So the Wasserstein distance is an approximation of the Earth mover's distance. And the way you can intuitively think about it is if you have two piles of dirt that are distributions, the Earth mover's distance is the cost of moving the dirt from one to the other to get them to be the same. So
where one set is going to be generated images and the other set is going to be real images?
Yes, exactly. So the piles of dirt are the generated images and the real images.
Levenstein distance for images.
Yeah, that's the way to think about it.
Sorry, NOP. So the small mini batch size is just a smaller mini batch size. That's all it is.
As far as I know, yeah.
Okay.
And it just destroyed. It's just showing that you
Don't do this.
Yeah.
The small is how small? How small?
I don't know. It says in the appendix. It's probably like 4 or something.
Good.
So how you, you're saying the convergence looks much better than, like H looks much better than E, F, and G.
Yes.
Why is that?
I mean, you can come up closer and look, but it's a pretty quantitative. It's a pretty qualitative thing.
Okay.
Why does a small mini batch destroy it? Like, is it just there's less variety in the batch?
Well, I
Can you
mean,
speak up? I didn't hear anything.
Like, why does a small mini batch destroy the training process? Is it because there's just not as much variety in the batch?
well, it definitely would make this mini batch standard deviation feature less useful. But the big reason is that with a smaller sample, you can get bigger gradient changes, and they might not be meaningful.
Okay.
One of the contributions of the big GAN paper, it's one of the newer papers from this year, goes into testing with very large batch sizes with GANs, and they found massive improvements there. So this is the other end of the spectrum.
I mean, if you think about it, if you have a very small mini batch size, the underlying tangent space of the gradient is going to be really nuts, right? And like as you span a larger chunk of the underlying distribution space, you're faking a smoother space almost as the sum over the expectation.
Okay, so like if you get 2 images in your batch, and then like they're vastly different images, then
it's effectively meaningless, right? You're like, oh, I should go in every way.
There's a similar technique that has been used with CelebA, which is if you're limited to small batch sizes because you have consumer grade hardware, let's say, then one option is to do experience replay, where you basically keep track of images from previous generator, like generator outputs, and then present the full set of like the history of generated images to the discriminator, and that can help. Where each cycle is still using a small mini batch, but the discriminator comes up with its gradient based off of a large number of past inputs from the generator. It also helps prevent the generator from cyclically fooling the discriminator, because if it's just bouncing back and forth between, say, 2 modes, then that's going to be evident in the history, in its history, in the discriminator.
So is that kind of analogous to kind of like the phasing in idea, like you?
That could be like I would imagine that. So analogous to the phasing in. Sorry.
Like you're just adding the new small mini batch on top of what the discriminator has seen up to this point.
Yeah, like experience replay is one way to kind of get the benefits of being able to go high resolution on smaller hardware, while at the same time being able to still get high quality gradients from the discriminator.
Right, since that's a comparative conversation,
Fair enough.
I suggest to postpone it.
Cool. Any other questions on the evaluation of this? So just to summarize, they find that everything they did made it better.
Convenient.
Why is MSSim bold, but it's showing the least value? Like
it's just that's the
oh, because it's
yeah,
distance.
It's just showing the best.
Is that so? Yeah, because it's distance.
Yeah.
Right.
0 is good.
Yeah, lower better.
Well, yeah, lower is better.
Cool. And things aren't as dramatic with the bedroom data set, but they play out the same story.
Okay. Okay, I object to this, the way you say similarity, because it seems like a distance than similarity. That's confusing. Do they call it similarity?
It's called
structural
multiscale.
similarity.
Structural
Okay.
similarity.
I object, but there can be discussions.
That's argumentative.
Okay.
That's I know. I'm gonna edit myself out of this.
Okay, maybe this is for discussion, but to the top right.
Yeah.
Why is that case? Because like the reason they did this whole thing is to kind of preserve some kind of structural integrity, right? Why didn't they outperform the baseline?
Because that's MSSI.
That's MSSM. This is the distance metric they produce.
But isn't that MSSM? Isn't that supposed to
That was the bad
give you
one.
like the coarser score on the bigger bits?
Yeah.
Is that?
So if
But one of their claim is that by doing things from small, they kind of preserve the structural integrity.
Yeah.
But why did it turn out worse?
I mean, they say, so they introduce not being happy with MSSIM because it's good at global things but not good at local things. But in this results, really what they're showing is that MSSIM isn't really good for anything.
Okay.
Or what it's good for. Or what it's good for is not the thing that they're improving via progressive.
Okay.
That's a better way to say it.
Yeah.
Just one question about the evaluation methods in general, GANs word.
Yeah.
Is there any human element involved in the evaluation metric at all, or?
I've read papers where they have a human qualitative section where they get people to rate images, but it's not a widely used.
Well, it's not used here.
It's definitely not.
Not
used.
here, but in general, I'm just.
But yeah, it has been used before.
The CelebA paper uses that basically where they present generated images and real images to humans, and then they have to distinguish which ones are real and which ones are fake. And it's kind of surprising actually for some of the high quality ones. Like they can fool a lot of people actually. It's pretty interesting. Yeah. At high resolution though, people can usually tell them apart. But
there was a deep fakes paper that came out about 4 months ago where they made videos of people and they'd say, make someone else say the words of a different person. And they found that they could fool like 30% of people with them, but then about 20% of people thought real things were fake too.
Fakes were passed by the discriminator, or mostly like in these quantitative methods?
I think they just show people generated images and real images and say which is the real and which is the fake.
So that's off context. Back to this one. So essentially what they're doing here is that they're coming up with a bunch of improvements and also come up with their own metric and say, oh, our improvements improve our own metric.
Yeah.
Is that?
That's how they're saying it, yeah.
Cool.
So, okay, very quick clarification. So that sliced adversarial distance actually works, and so it correlates with the quality of the images.
That's what they're finding, yes.
But only for their images or for all images?
They haven't shown any results outside of their images.
Yeah. Okay. Not a lot of people are using it either.
It hasn't been picked up, from
No.
what I understand.
Okay. Amazing.
Just
And-
to add a point to
yeah.
that, I think it's hard to get the that data set, the HQ version, CelebA HQ.
Yeah.
It's not easy to get.
I think it's readily available from their GitHub page.
I tried
It's just
finding
how
all of it.
big it is.
It's
Okay.
it's
Is
very
the issue.
complicated to use. Yeah.
Okay.
Right, and it's not just like a bunch of high quality PNGs.
Yeah.
I haven't actually used that data set.
Yeah.
Yeah, I forget what format it's in, but
Yeah, I remember I tried to get
You
it
need
once
to-
and
I
then
think it's a
I just
pass.
couldn't get it for some reason. There's something with it that I couldn't use it.
Okay, beautiful. Discussion point.
and these are some of the other results that it came up with. This is if you train it on motorcycles. I find the results with objects aren't as good as the results with faces. These, on first blush, they look really real. But after about a second or two, you can start to see like the proportions of this are just a little bit strange. Or when you first see this, it looks like there's a rider, but there's no actual rider there. It's just like goop.
It's very shocking.
But you do get to see that the resolution is stunning, and that it's really head and shoulders above other things that have been presented. Now there have been some new things that came out, but back in October 2017, this was a massive step forward. And these are boats. And the boats look better than the motorcycles, actually. Yes, right.
Why the background in these ones is my curious. Like the faces, they never showed a background, but it seems like in this one it has to do extra work to not just get the image, but also generate the background as well.
Yeah.
The variance is a lot more controlled in the face stuff. They're all centered.
Yeah.
They're all cropped.
Because I looked at these earlier, and I was like, wouldn't the results be better if every shot was on a green screen of a motorcycle? Like, not with
Yes.
a background?
Yeah.
Because, like, think about the extra labor. It's got to also, like, make the image, and then, like, the background, too.
Yeah.
And
Then it's another area for mode collapse too.
Yeah.
It's really possible to just generate against very similar backgrounds.
Still impressive. Like, you got a background that looks normal. Yeah, like, that one with the sunset is beautiful.
Yeah.
So, conclusion. The progressive growing of GANs paper introduces a new training procedure that gradually increases the resolution of images going through training as the training progresses. This has a lot of benefits, namely that you can pass a lot of images through quickly, you fix the problem of the discriminator and the generator being too far apart early in training, you're able to train to very high resolutions. They introduce Minibatch standard deviation and 2 normalization techniques, equalized learning rate and pixel-wise vector normalization. And they also show that according to their metric, they improve the results. They propose the sliced Wasserstein distance as a more consistent alternative to the MS Sim. And finally, they observe results that are at least as good as anything else that was published at the time, and for faces that are head and shoulders better. So now, Michael contributed a few points that we could potentially look into criticizing the paper.
And we're gonna, sorry, Gordon, go on. So we're gonna take a 2 minutes break and then start.
Cool.